Okay, so we were discussing the effect of temperature, and so far what we have seen, let me summarize it in a bit. So, we were looking at and we found that it is a kind of very complex behavior in the sense that temperature affects N and K in the power law equation, and hence it affects the overall flow stress. Temperature also affects M, which is the strain rate sensitivity, and hence it affects strain rate, sorry, not the strain rate, but the effect of flow stress due to strain rate, like in here it is flow stress because of strain. Now, the temperature effect onto stress and strain is not one way. In fact, stress and strain can also have influenced temperature, and if you put it like this, the total work done, almost 99% of the work done when you are doing any deformation gets converted to heat energy, and therefore, that heat energy is nothing but temperature rise inside the material. So, if you were to look at so rho Cp times delta T would be the total work done or total utilization of work in terms of temperature, and sigma bar times d epsilon bar integral is the total work done per unit volume, and alpha is a proportionality constant showing how much heat is going into the material. It could be getting partitioned, some of it may be getting radiated away, or it may be taken away by the tool or something like that. So, alpha represents the amount of heat or the fraction of heat that goes into the material and which will lead to temperature rise. So, now you see that temperature not only influences stress, the stress and the strain values in turn also influence temperature, and therefore, the relation between temperature, stress, strain rate are not linear to say the least. So, there is a complex interplay, we can put it like that. Strain rate and temperature, the three parameters, which in turn will influence the flow stress behavior. So, there is a complex interplay that we see now. Now, once we have seen the effect of temperature, we also talked about that there is an origin for this, and the origin is that temperature influences microstructure, the structure at the micron level. So, things like your defect distribution, phase distribution, interfaces, these all get influenced by temperature, and because of which we see all the different influence of temperature on the stress, strain rate and so on. Now, that we know that there is effect of temperature or in the stress strain affect temperature, it is time to look into why we have the three domains. Why actually we have already discussed the why part, but to look at it you can say to look at it in a little bit more detailed way. Why we have the three different zones, you remember the three different regimes, the cold work, warm working, let me call it working, the hot working. So, the next part is we will look at each of these separately. So, let us start with cold working. What is cold working? By now, you would have realized cold working is nothing but when you are doing the deformation or metal working at temperature less than 0.3 Tm. What is Tm? Is the melting temperature expressed in Kelvin. So, there is a point So, we are looking at it as a homologous temperature. So, when the homologous temperature is less than 0.3, then the work that we are doing is called cold work. There are some certain characteristics associated with cold work. Now, let us look at what are those characteristics. Since we are doing the cold work at a temperature less than 0.3 Tm, where you remember there is no recovery or recrystallization taking place in the microstructure. So, that is one characteristics of cold working, that there will be no recovery and recrystallization. That would mean if you are not recovering and there is no recrystallization, it means that when you are doing the deformation, the material is getting work hardened and therefore, more and more stress is required. So, the load requirements are high. And it is related to the fact that no recovery or recrystallization is taking place. Remember, recrystallization is what? In simple terms, it is the creation of new strain free grains. If no new strain free grains are getting formed, these are old strained work hardened grains, and therefore, you need more and more or higher and higher stress to deform to a higher level, to a higher strain value, and therefore, load requirements for cold work is high. On the other hand, you have, because you are doing it at a very low temperature, therefore, the expansions are not there, or basically you do not need to see how much the material will contract after you have cooled down, because you are already at a very low temperature, and hence what you get is better dimensional control. Another aspect is again related to recrystallization fact, that there is no recrystallization taking place when you deform the material, and if you are doing the deformation in such a way that the material is getting deformed in one particular direction. So, at the microstructure level, the structures which we call as grains will get a directional structure. You can say they will be elongated in one particular direction, and because of that you will have directional properties in the component formed by cold working. So, these are some of the important characteristics that we know, and there is I missed one of them, which is better surface finish, because we are not doing it at higher temperature. As you would see that at higher temperature what happens is that some scaling forms, because the material is prone to oxidation, but in here, since you are doing it at room temperature or close to room temperature, at least in terms of the homologous temperature, you are at very low temperature, and therefore, you get better surface finish. So, most of it that we have discussed here for the cold work are its advantages. Now, let us also look at some of the negative points or the disadvantages when we are working with cold, or when we are deforming a material to cold work, and one of them actually I have already listed out there, and that is high load requirement. So, what is the drawback of high load requirement? It would imply that you will have to have equipments or much equipment with much higher loads. So, you will require heavy equipments. In terms of cost, it would mean larger capital intensive. So, heavy equipment required. So, now we are looking at drawbacks of cold work. So, you need heavy equipment because the load requirements are high at for the cold work, no recrystallized grains are forming. You have to keep increasing the load as the material gets deformed further and further. Another thing is that again related to, of course, all the properties have to be related with the microstructure. So, the microstructure, since it is not getting recrystallized, it would mean that it is getting more and more deformed, it is getting more and more defects, and very soon it reaches a point that you cannot deform it further, or it will start to create cracks, or the material component will have defects at the component level, not at the microstructure level. At the component level, you may start getting defect, and that means it has limited ductility. And another important disadvantage of using cold work, when we looked at the microstructure, we also saw that residual stresses do not get relieved when we are doing, or when we are at a temperature below 0.3 Tm. So, large residual stresses. In most of the cases, these residual stresses are responsible for causing a deteriorated property of the material. So, another important disadvantage is large residual stresses, and as I said earlier that when you have component manufactured using cold work and it has very large residual stresses, what it implies is that those components can generate defect very easily, particularly it may fail very quickly or at a much lower frequency under fatigue stresses. So, this kind of reduces or limits the life cycle of a component. So, that is one very big disadvantage when we are using cold work. So, now having discussed cold work, now let us move on to another, or the other extreme, which is hot working. So, right now we were dealing with temperature less than 0.3 Tm, but now if we move on to the hot working, we are in the temperature range above 0.5 Tm. So, first thing is to understand that it is characterized by temperature greater than 0.5 Tm, and remember again I have to emphasize it again and again that we are talking, when we are putting the temperature like this, the temperature is in Kelvin. So, the temperature must be used in Kelvin, and 0.5 of that, when you are above that temperature in Kelvin, is that we are talking about hot working. Other characteristics of hot working are that since you are above 0.5 Tm, it implies that old grain structure is destroyed. And new strain free grains exist. It is as if these grains do not have any history of deformation. So, that is why it is called strain free. These are absolutely new grains which are recrystallized, which have formed inside the material, exist or are formed when we are doing the deformation at temperature above 0.5 Tm. Now, another thing we know for temperature, when the temperature is very high, we know that stress requirement will be high, and therefore, low load requirements. So, this is also an advantage. So, you can deform a material. So, this fact that requirement of the load is lower, it implies that very hard or difficult to deform materials can such materials can also be formed, given shape, using hot working. So, that is possible only because our load requirements are much lower at higher stresses, at higher at higher temperature, and the temperature we are looking at is above 0.5 Tm. And at 0.5, if you remember from the micrograph plot that I drew in the previous lecture, you would know that residual stresses are almost negligible. So, residual stresses are not present when we are working at high temperature. And since the grains are new, in the cold working we saw what, that the grains will have directional structure, because they have deformation, they will be rolled in one particular direction or they will be deformed in along one particular direction. Therefore, they will have inadvertently some directional nature, but here the grains are forming new, the new strain free grains are forming, and therefore, when these new grains are getting formed, they will not know any particular direction, and therefore, they will be what are called as equiaxed grains, and this equiaxed grain imply non-directional properties of the component formed by hot rolling or hot working. So, in most cases this is a advantage that you have non-directional properties. In some cases you may want to have directional properties, and we will look at some example as and when we get to those things. And another very important aspect of hot working, I will write it over here. So, we have seen that high effect of high temperature, we need low stresses, that has already been given here. We also know because the effect of high temperature is higher strains are possible or higher ductility is possible. So, it means that intricate shapes which require much larger strains can be formed. So, these are the major advantages that we know for hot working. Of course, there will be quite a few more that you can come up with, but these are some of the most important advantages, and these are most of the things that you can relate that you can see here are related to the fact that you have recrystallized grains formed when we are dealing with hot working. So, the strain free grains are present there, because of this the load requirements are lower, and because of the same thing you are able to get much higher ductility, and therefore, intricate shapes are formed, and because of the same thing residual stresses are negligible or not present, and then you have non-directional nature or properties of the component that are formed using hot rolling. But there are of course some disadvantages also related to hot working. It is not that if hot working were everything was good about hot working, then all the components would be formed using hot working, but we know that it is not true. So, let us look at some of the disadvantages of hot working. And one thing that you can quickly say is that since we are doing the deformation at higher temperature, so high heat requirement, heat energy requirement, which is a drawback, because it implies that heat energy is what is you can translate in terms of industry as cost input. So, you have to provide so much, if you have to heat a material for say 1 hour at 800 degrees Celsius, that implies so much of heat energy or so much of electrical energy will get invested into the material. So, high heat energy requirement, which is a major drawback. So, that is not the only drawback. We also know that at a higher temperature materials tend to get oxidized. So, there will be some scaling behavior. So, tendency to oxidize and form scales. What else can we look at as the drawback? At higher temperature, another important drawback is that you may be using some dye, and in the dye you try to give the shape, but the material and the dye, they do not have good there may always exist some friction, and for that we add lubricants. But at high temperature it becomes difficult to ascertain what kind of lubricant will work, because the temperature is very high, the lubricant will either evaporate or it will get or it may become inflammable. So, lubrication at high temperature becomes a problem. And in the cold work, we gave one of the advantages as good dimensional accuracy, and that was possible because there was no change, or that material did not have to come back to room temperature, and therefore, you did not have to adjust for the change in the dimension. But that thing is not true over here. Here, if you form the component at a much higher temperature, when it cools down, there will be contraction, and therefore, there will be some inaccuracies in the dimension. So, dimensional accuracy is not high. And one of the other last one I will mention for that as a drawback of hot working, we know that there is a tendency to oxidize and scale, which means that it will also have poor surface finish. So, in effect what you will see is that hot working and cold working, whatever advantages we listed in cold working becomes a disadvantage in hot working, and whatever disadvantages we mentioned in cold working becomes an advantage in hot working. And that is why, in order to get a compromise between these two, we have what we call as warm working. Of course, there is origin to that, microstructural origin. We know that at this intermediate temperature, which we call as hot working zone, a phenomena called recovery takes place. So, the compromise for hot working and cold working is warm working. And what are the advantages of warm working? On one hand, you do not require very high load, nor do you require very high temperature or high heat energy input. To be precise, let me put it as heat energy input. So, there will be of course some amount of additional heat energy required compared to cold working, but it is not as high as that required in hot working. Similarly, the load requirement is not very high, but it is still higher than what will be required for hot working. So, it is if you are trying to get a compromise, then you also have to make a compromise in terms of load requirement and heat energy requirement. And the advantage is that you get intricate geometries as almost as good as you would get in hot working with good dimensional accuracy. So, now you see we are getting best of both the worlds. Good dimensional accuracy is not related with hot working, and intricate geometry is not related with cold working. But if you go for a high a little bit higher temperature, which is our zone of warm working, then we are able to get both. We are able to get intricate geometries with good dimensional accuracy. We are able to get good ductility without much heat energy, without heat input. In cold working there was limitation because the grains do not the grains keep accumulating the dislocations or the defects, and eventually it will break. But when you are doing the deformation at warm working, what happens is that the material is able to relax, you can say, to put in quotes, to certain extent. And why is that? Because the dislocations form cell walls, they are able to minimize the energy in the microstructure by forming cells and cell walls, and therefore, you can say that the material is in a better position to accommodate more strain, and therefore, you are able to get a little bit higher ductility than you would get in cold working. Very little scaling. So, although we are using high temperature, relatively high temperature, and since we are using a little less high temperature, less thermal shock to the tools. Remember, if you are working at high temperature, even your tools get exposed to those temperature, and that is, if you start from a cold temperature to hot temperature and then again bring it down to low temperature, it is called thermal shock. So, less thermal shocks of those kind for tool materials. So, it is a good compromise between the two, but it is still not that this is best or this is the only option available to you. For example, in some cases you may still have to go with cold working, in some cases you may still have to go with hot working, depending upon the requirement that you have. So, these are just take the three as three different zones of temperature at which working is done to get different kinds of properties and for different kind of material. For example, let us say if you are working with aluminum, which has very low melting point, then why do you need to go to very high temperature? Even the room temperature is sufficiently high for that, and therefore, you can, in fact, all the window frames that you see made out of aluminum, they are extruded at room temperature. On the other hand, if you want to work with a hard material like titanium, then and you want to do some extrusion for titanium, then you will have to deal with, or you will have to work at higher temperature. In that case, hot working becomes a necessity. So, there is no hard and fast rule that this is the temperature you must use. It depends on a combination of several factors, including the properties of the material, of the component that you require, the properties of the material that you are exposing to or that you are trying to deform, and so on. So, now just take a small example here to understand what is exactly cold working, hot working. Let us take a material like lead, which has a melting point of 327 Celsius. So, this is temperature, melting point temperature of lead. Now, if you want to put it in, first thing we need to do is put it in Kelvin. So, this is 327 plus 273 equal to 600 Kelvin. Now, what is the 0.3 Tm for this? 0.3 Tm for this will come out to 180 K, which is in Celsius it will be minus 93 degrees Celsius. 0.5 Tm for this lead will come out to 300 K, which is equal to 27 degree Celsius. So, you see, if 0.5 Tm for this is actually what is a room temperature for us. So, one thing is important is to understand that when we say hot working does not mean you have to elevate the temperature. It is related to the melting point of the material. Now, let us say you were doing the rolling of this in winter when the temperature is 20 degrees Celsius. So, you are working at 20 degrees Celsius and the 0.5 Tm is 27. So, you are actually in the warm working zone, or you are deforming the material like a warm working. If you were doing the same experiment in summer when the temperature is, let us say, 40 degrees in your lab, so this is higher than the 0.5 Tm, and therefore, what you are doing is actually hot working. So, this is a simple example that we have. So, we will leave it at this point over here, and we will come back in the next class, and we will talk about the mechanics of deformation. So, we have dealt with all the basic parameters for deformation like strain, strain rate and temperature in different ways possible. Now, it is time to move on to the next step, which is to understand the mechanics. So, we will meet in the next class and discuss mechanics. Thank you.